manages a group of 40. That is a large group, and 50% of them are women at Imperial College. And then in just last year, 4 of her members has prestigious awards. I can continue and continue, but Prof, thank you so much for today, and we hope to listen to your talk and also be able to ask questions. We also hope that that will be a good opportunity for all the young people that are listening to probably reach out to see if Prof, because she will be available for some supervision or mentorship in the future. So Prof, over to you. Thank you so much. And then please go for it. And thanks for coming.
Thank you for inviting me. Yeah, it's very nice to be here and give this presentation. So yeah, without further ado, I will start. Let me see if I can. Yeah, so basically I wanted to tell you in a nutshell that in my group, we are turning waste on one hand into advanced materials for batteries and fuel cell, and on the other hand into hydrogen and chemicals directly, and we're using various processes to do that. And why we do that is, of course, to address this important energy trilemma that we have, which is building new technologies for the future where we can move to a cleaner future free of fossil fuels with no CO2 emissions. But while doing that, we need to be very much aware of the cost of these technologies, their efficiency, but also what materials do we use to build these new technologies, because a lot of these materials contain critical metals, which of course a lot of these critical metals are in Africa, and that's on one hand good, but on the other hand is very bad because there's still a lot of exploitation going on, and the reality is that we don't have any of these critical metals here in Europe. So I think it would be good if we could actually build these new technologies without relying on them. So in my group, we do really a lot of things, and I won't have time to go through all of this, but I thought I'll give you an overview of some of my research activities going on. So of course, we work a lot on carbon materials. We do non-porous, porous carbons. We are very good at varying precisely the pore sizes, the functionality. We also do carbon fibers from lignin. But not only carbons, we also do metal nanoparticle, funnily shaped metals. We work with metal oxides as well. We do even bimetallic and some organic. And as in every synthesis lab, we like to have this loop between material synthesis, understanding every single property that they have from atomic scale to nanoscale and macro scale, and then apply them for various applications. And of course, we also like to work hand in hand with modelers that can really help us predict some of their properties for various applications, but also help with some characterization tools as well in terms of the structure of these materials. In terms of applications in my group, I have really 2 streams of research. One is electrochemical energy storage, so batteries. And here we like to do sustainable batteries that are going beyond lithium ion. We're still doing a lot of supercup work, but also moving towards sodium, potassium, aluminum batteries, this type of new anode-free batteries, also based on sodium ideally. We do a bit of lithium sulfur batteries where basically you have a more sustainable cathode, and we're trying to minimize lithium at the anode. Then we also work on some silicon anodes for lithium ion batteries. Now, the other half of my group works on electrocatalytic processes. So we work on fuel cells where we're predominantly looking at the cathodic oxygen reduction reaction. We also do water electrolysis, looking at oxygen evolution reaction. But more recently, I'm very passionate about producing chemicals and fuels sustainably using electricity from either CO2, or we also do nitrogen reduction to ammonia, or biomass oxidation to various products. Now, I'm in a chemical engineering department, and because of that, I have fantastic colleagues that are experts in life cycle assessment and process engineering. And so they help me from very early stage of my data to look at the sustainability and impact on the environment of some of these technologies that we develop and some of these materials from very early days, and also to look at the feasibility of their cost from very early days based on lab data and extrapolating to larger scale. And one direction that I really want to move my group in is to do these high throughput experimentations and build a digital lab for batteries and electrocatalysis, where you will have robots assembling your coin cells, robots testing your catalysts, and you will have researchers that will just simply program the robots and use the time that they spare in doing these tedious experiments to look up for knowledge and pretty much teach the robots what to do. But also, of course, with such a high throughput, we need data management, electronic data, and machine learning to use the best of the data to accelerate materials discovery for batteries and electrocatalysis, but also optimize performance. So as I said, we kind of do a lot of things, but what I want to tell you today is I want to tell you 3 things. If I have time, I might not have time to tell you these 3 things because I really need to go at 4. First thing is how we produce green hydrogen and chemicals from waste electrolysis. And then I will touch on the single atom catalyst for oxygen reduction reaction. And maybe if I have time, I will tell you a bit about batteries beyond lithium ion as well. So let's start with glycerol oxidation to lactic acid. Well, we all know that hydrogen is a very important vector for the future. We probably all know that hydrogen comes in different colors. Gray is the one we don't like, it's made from fossil fuels. Blue is the one that I personally still don't like because it's also made from fossil fuels, but with carbon capture and storage. So it's just an excuse for fossil-based companies to do the same thing, business as always. Turquoise is made from biomass, but you would still emit hydrogen. Again, not the biggest fan. What I'm the biggest fan is really trying to move towards green hydrogen, where you have no CO2 emissions while you generate this. Now, hydrogen is the wonder vector that at least the UK wants to use across all the sectors of the economy to decarbonize it. From transportation, we're using fuel cells or alternative fuels like ammonia, to actually changing the infrastructure in buildings for having hydrogen boilers, to industry where there is a lot of need of hydrogen, and most of this is gray hydrogen to produce chemicals and materials, to agriculture where ammonia fertilizers are key. So as you see, this is kind of a map of the UK, and these are some points where basically green and blue hydrogen production plants will be placed. However, these are always associated with this huge power the UK has for renewable energies based on wind, because it's just an island. Now, of course, because it's just an island, what would be nice to develop is also ways of producing hydrogen directly from seawater, but that is technology that maybe is on the lower scale of technology readiness level, and there's still a lot of challenges there. Now, to produce green hydrogen, of course, people are looking at water electrolysis. And so depending, of course, on the type of the electrolyte you have in these electrolyzers, you can have a traditional alkaline electrolyzer, which uses a very concentrated KOH solution. These are commercially available already for a while in Japan. They're not the most efficient, but they work. I think the wonder of electrolyzers and everything that everyone is seeking is this proton exchange membrane electrolyzer. This is the most efficient technology of all of them and uses this Nafion conductive polymer electrolyte in between the anode and the cathode. However, it starts to be a problem because Nafion contains fluorines, and at least Europe legislation is moving towards fluorine-free chemical compounds. So if somebody could come up with a a membrane that would be as conductive as Nafion, that will be amazing, and probably that person will get very rich very soon. So, I strongly advise you to do research on this. The solid electrolytes, solid oxide electrolysis, this operates at high temperature and uses a solid oxide that is conductive to oxygen anion, and has been popular in the past, is declining in popularity. And then also something that is quite popular is alkaline membrane electrolysis, where the bottleneck was that there weren't good enough OH conductive membranes on the market, but this has rapidly changed, and we have quite a few candidates now. And the nice thing about this technology is that you don't need to use critical metals for the oxygen evolution reaction at the anode, but then the kinetics on hydrogen evolution here are a bit slower. Nevertheless, if we take, for example, PEM electrolyzer as an example, and you go through a cross-section of this, you would see that the anode is composed of a iridium oxide layer that is quite thick, which is deposited on a porous titanium. This is the conductive Nafion in the middle, and then you have a little platinum deposited on carbon at the cathode. Now, if you look at the thermodynamics here, potential versus current, you see that most inefficiencies come not from the hydrogen evolution reaction, which happens at the cathode, and here you need as little as 0.05 milligrams per square centimeter platinum for a very low of a potential, but really for the oxygen evolution reaction, where you need quite a lot of iridium catalyst, and you would still get significant of a potential. Now, this reaction here at these potentials is extremely corrosive, and so if you would have a carbon support here, this would be completely oxidized. So a lot of cost comes also from using this titanium porous layer, which is very, very expensive. So both the titanium and the iridium are making quite a big portion of the cost of this PEM electrolyzer technology. Now, of course, there's different ways of doing this, but my view on this is, can we actually electrolyze something else than water? And if you look in nature, there's a lot of molecules that you can derive from biomass, and all these molecules contain quite a lot of protons. So the idea is, can we take some of these biomass-derived molecules, and instead of oxidizing water at the anode here, as you normally do in an electrolyzer, you will partially oxidize one of these biomass compounds to a specific chemical. And on the other side, you would still happily evolve hydrogen as in a classical water electrolysis on platinum. And so here you would actually have very favorable thermodynamic kinetics. And the nice thing is, if you look at biomass compared to water, you would see the potential at which these oxidation reactions happening are much lower. So overall, the bias that you need to put in this electrolyzer, the electricity, is much lower because of the low potential. So that would give you quite a lot of savings in the cost of hydrogen you would be producing compared to the one from water electrolysis. And I forgot to say that that's a big problem, and that's why green hydrogen is not implemented today, because it's still very, very expensive compared to gray hydrogen. Is about 10 times more expensive. So we need to bring the cost down in order to be widely adopted in industry. Now, another advantage of this is that, when you oxidize water in non-water electrolyzers, you would make oxygen, which is not so useful, really. But if you could make a high-value chemical here, that would be really good, because not only that you produce green hydrogen, you would also produce a valued product. And so, of course, we are focusing on this because this reaction that's happening on the anode is key to the whole thing. As I said, the hydrogen evolution is very well known and it works well. So we started with glycerol, and glycerol, as you may know, it is a waste product from biodiesel industry. So, you grow special plants. This is this raps oil, and you do biodiesel through a biorefinery where you produce your biodiesel, and as waste you get glycerol, and nobody has many uses for it. So it would be good if we could turn this glycerol into, you know, high value products in a circular economy type of fashion. So when we start doing this work, we've published this paper in ACS Catalysis. This was done by some very talented postdoc that I have, Hui Luo, who's now a lecturer at University of Surrey in the UK. And she thought, you know, based on the literature, that if you use platinum, works the best for glycerol oxidation and does it at a very low potential, but it gets easily poisoned by CO that you would generate during the oxidation of this. So she thought that we could modulate both the selectivity and increase the resistance to poisoning of platinum catalyst by adding some nickel into it. And I don't have time to go in detail, but in particular, what Hui made was a pure platinum catalyst. And then she made a catalyst where is a bimetallic link between platinum and nickel, but you have an excess of nickel. Then you have a catalyst where you have one platinum to one nickel atom. And then you have a catalyst where you have, here you have an excess of platinum, and here you have an excess of nickel. And if you look at the graph in oxidation of glycerol, and you look for the selectivity toward this product, glycolate, you would see that basically what happens is the more nickel you have in the system, the more you're likely to absorb this glycerol on the surface of your catalyst via all free carbons, and therefore you generate carbonates. And you also see that if you have one platinum to one nickel, it seems that this is the catalyst that delivers the best mass activity as well as the best specific activity. We also went to do some more mechanistic study to understand, you know, what happens to the catalyst during the electrocatalysis process of biomass oxidation. So we developed this inoperando cell that we take into synchrotrons where we shine X-ray through this. So we went to different synchrotrons, one in the UK, which is Diamond Light Source, and one in France, which is the ESRF, the European Synchrotron Facility. This is the cell that we developed. So we have here our working electrode. We have our reference electrode here on this side. And then basically here we have our counter electrode on this side. And here we are flowing the electrolyte. This is how this cell looks when it's mounted in operando. And then what we collect is this SAINS spectra, where basically you're looking at the nickel KH. And you would see whether this nickel is oxidized or not. And what is interesting is that when you look at the nickel KH with SAINS, you would see that when you don't have glycerol in your system, you really oxidize your nickel on the surface of the catalyst all the way to nickel oxyhydroxide. So you have a platinum nickel bimetallic. When you do the glycerol oxidation, under those oxidative conditions, you'd form anyway nickel hydroxide, and this goes all the way to nickel oxyhydroxide. So you clearly see a change in the increase in the oxidation state of nickel, and you can nicely see this via spectroelectrochemistry as well. When you have glycerol in your system, it seems that glycerol really absorbs and stacks on your catalyst, and it prevents this nickel to further oxidize to nickel oxyhydroxide. So you will maintain this nickel oxide islands on your catalyst, and this nicely correlates with spectroelectrochemistry where you see no change as well. Anyway, this was a nice study, but we couldn't really control the selectivity on any of this catalyst towards a particular product, and we got a mixture of acids. So then we wonder ourselves, what do we want to really make from this reaction? And ideally, I told you that we want to make selectively one product, not a million of products as we got from this paper that we did here. So then if you look at the market price versus the market size, you would see that would be quite economically viable. You could do lactic acid. And so we thought how we can actually selectively electrooxidize glycerol to lactic acid. And so we did some lessons by looking at the literature, where we've learned there are actually two pathways. There's a chemical pathway, and there's an electrochemical pathway. Now, on the electrochemical pathway, what happens is you have glycerol. This glycerol forms dihydroxyacetone. This is in equilibrium with glyceraldehyde. And once you form this glyceraldehyde, it oxidizes to form a mixture of tartonic, glycolic, glyceric acid. So pretty much all this that we observe with our platinum, nickel, and platinum catalyst via the electrochemical pathway. Now, the trick of making lactic acid is to actually form dihydroxyacetone and stop it here. And don't form glyceraldehyde. So stop this equilibrium to form. And once you stop this, the dihydroxyacetone is formed. You can have this chemical pathway to form 2-hydroxyacrylaldehyde, and then via a rearrangement in alkaline environment, you'll form lactic acid. So the question is, how can we actually promote the path in red? If you do some energetics, so you look at Gibbs-free energy of all these different intermediates and how they would absorb on platinum 111, you would see that you would have the path in blue, and these are the energetics for pure electrochemical, and the path in red, which is actually a mixture of electrochemical and chemical pathway. And so we want this pathway, which is a mixture of electrochemical and chemical pathway. So in order to have this achieved in a real catalyst, the idea was to still use platinum, and the platinum nanoparticles would do electrocatalysis of glycerol to dihydroxyacetone. And we want to stop the electrochemistry here and then have the rest happen chemically. And so in order to do that, the catalyst that would basically take this dihydroxyacetone and convert it to pyruvaldehyde would be something from the literature that would have a lot of Lewis acid group. So we supported platinum on different metal oxides with a lot of acid groups, and we looked at lactic acid production, and we saw that that scales very nicely with the amount of acidic groups on the surface of the catalyst. This fitted also very nice with TFT calculations, where basically if you take the Gibbs-free energy of glyceraldehyde, the product you don't want to form minus the Gibbs-free energy of hydroxide, this fits very nice also to lactic acid production. So following this concept, we have managed to produce 64% of lactic acid from glycerol electrooxidation in an electrolyzer, while on the other side, on the cathode, we are happily generating hydrogen with an efficiency of 26 versus 51.2 kilowatts hour per kilogram hydrogen. And this is the value that we estimated from water electrolysis. So this was a very nice story. Inspired by this, we then looked at plastic depolymerization as well to make terephthalic acid, glycolic acid, and hydrogen. So our process in a nutshell is the following. We're taking West PET. We are doing a depolymerization process whereby we add some solid sodium hydroxide flakes to it, and we shake it a little bit with mechanochemistry. And what we get out of this is we get terephthalic acid, which is the monomer of polyethylene glycol, ethylene glycol, and sodium hydroxide. Then we're putting this, we separate this using electrodialysis back to sodium hydroxide, which we're using back in our depolymerization, terephthalic acid, and ethylene glycol. And so we could stop here, right? And we could have this process in which we say, you know, to PET producer, Pepsi, Coca-Cola, look, we can give you this technology. It's really cheap. We can take PET and make it into its monomers, which we give you back to you to make new PET bottles. But a techno-economical assessment showed that our process would be much more economically viable if we could also take this ethylene glycol that we produce from the depolymerization of PET, which has a very similar chemical structures to the glycerol, and then put this through an electrolyzer to produce glyceric acid and hydrogen. And so we have 3 people, Enrico that's doing the depolymerization, Ding Chang that works on the electrodialysis, and Helen who's doing the electrolysis. So as I said, our process for depolymerization is relatively cheap. We are using these PET flakes with sodium hydroxide. We have a resodyne acoustic mixture, and then we're aging the system for some time. We are trying to improve the kinetics here, and we're getting sodium terephthalate and ethylene glycol. We are also doing a design of experiments optimization to really improve the parameters for depolymerization, such as aging time, temperature, humidity, mixing time, and so on. And this is our design of experiments. And what we've learned from this is actually that we have the best aging conditions maximized, which is 60 degrees, 72 hours. But this is still a bit slow, but it's simple. So we're looking at other methods to invert the speed. We're also looking at different PETs, some clear PET that we get from Starbucks cups in the campus, from green PET that we get from San Pellegrino bottles, some mixed PET that we get from a real plastic recycling company. So we still have a lot to do to optimize the depolymerization. Now, once we do the depolymerization, normally the conventional separation to get every component out of the mixture of sodium hydroxide, terephthalic acid, and ethylene glycol would be to extract ethylene glycol with acetone. So now you extract your ethylene glycol, and then you are left with a mixture of sodium terephthalate and sodium hydroxide. You add sulfuric acid to this, and you crystallize the terephthalic acid, and then basically you get sodium sulfate, which then you add sulfuric acid, then you add again sodium hydroxide. So it's quite a complicated process. Now, we are overcoming the separation of all these components by doing this electrodialysis process. And we have 2 different ways of doing it. One is with 2 different membranes. So one is with 1 membrane and 1 bipolar membrane. And we separate nicely and efficiently all this, but I don't have time to tell you in detail about all these processes. And then once we separate everything, as I said, we take ethylene glycol, we put it to an electrolyzer, similarly to what we do for glycerol, and we make with quite high efficiency glycolic acid out of this. Now, glycolic acid, it's a very valuable chemical for cosmetic industry. It's in a lot of expensive creams. There is now this company from US, it's called The Ordinary, that sells glycolic acid solutions directly to tone your face and have a wonderful skin. So that's our market. And then we're also producing hydrogen at the same time. And to do this electrolysis of ethylene glycol is much easier because you have 1 less carbon. So in fact, if you do it on platinum and gold, you still get glycolic acid with quite high selectivity. So I guess on platinum, you get better hydrogen. On gold, you get better glycolic acid. But you could do this at relatively high current densities, quite selectively towards this glycolic acid, which is nice. So to summarize, our biomass valorization to high-value chemicals with electricity is that we take waste residues from biodiesel, which is glycerol, and we turn it into lactic acid. And lactic acid is the biggest monomer precursor for the production of polylactic acid, which is a biodegradable polymer. And most of the products now in Europe, whether you go to a picnic and you know, you buy all these plastic forks and plastic cups and coffee cups and bags for your bio garbage or bags from the supermarket. They're all now made from polylactic acid because they are fairly biodegradable, although, you know, the biodegradability of this only happens in special plants. If you leave it on the street, it would still persist in the environment quite a lot. Now, I also showed you how we actually take plastic waste and through some smart depolymerization and electrodialysis process, we turn this into terephthalic acid and ethylene glycol. And ethylene glycol we convert to glycolic acid, which again, a phase toning compound and gives you this wonderful skin. And then another thing I didn't show is that we also work on converting biomass to 5-hydroxymethylfurfural, which we then electrochemically oxidize to furan decarboxylic acid, which is a precursor of making green hydrogen and this PEF, polyethylene furanoid, which is a fully bio-based PET. So this is our work on hydrogen production electrochemically. I only have 30 minutes left, so let's see how much I manage, but I want to tell you maybe a little bit about this oxygen reduction reaction in fuel cells. So I told you how to make green hydrogen. Now we have this green hydrogen, we could put it in a fuel cell to produce electricity and water with no CO2 emissions. The way this works is that you put hydrogen through a fuel cell, you have an Naphion membrane that conducts proton in the middle. Hydrogen is oxidized here to protons that are conductive via this Naphion membrane and electrons that go on an external circuit, so you generate your electricity. Now you put in at the cathode oxygen, which you then reduce to produce water as your only product. So this here is the oxygen reduction reaction. Now, if an electrolyzer, the water oxidation happening at the anode was the kinetically limited step, in a fuel cell is the other way around, where this oxygen reduction reaction is very slow. And the way it works is you have a membrane electrode assembling where you have your carbon support, normally with some platinum nanoparticles, and the membrane. So you have a lot of interfaces here between the membrane and your active electrode, between your catalyst layer and the carbon support. And also because you have liquid, solid, and gas, you have even more complex interfaces. Now, as I said, normally for fuel cells to catalyze this oxygen reduction reaction, you use platinum on carbon. But very popular to replace the use of platinum, which is also very expensive, like it is iridium oxide for electrolyzers, you have the opportunity to do this single atom catalyst, which is basically a molecular catalyst, which is one iron atom coordinated to 4 nitrogens supported on a conductive carbon. So the advantage of this is on a high atomic efficiency because it's almost like having a molecular catalyst, but in a heterogeneous catalyst form, and because it's on carbon is also conductive. I'll skip this slide and I'll tell you a little bit how you would synthesize this iron nitrogen carbon catalyst. So in the literature, what most people do is they throw in a furnace an iron precursor, a nitrogen precursor, and a carbon precursor, and they hope that miraculously the carbon will be doped with nitrogen and the iron will be coordinated to these nitrogen sites. But in reality, what happens when you do this directly at high temperature is that you form a lot of different active sites. So the iron you throw there, it would also form iron carbide. You can have some single atom sites, but also very easily you could form some metallic iron and iron oxide. So you don't have very well-defined active sites within this catalyst. You have a zoo of active sites, some single metals, but also a lot of others. Other approach is to first just dope the carbon with nitrogen, and then try to throw in the iron that would be coordinated to nitrogen. But this is also quite difficult, and you get an unstable mixture of iron nitride, iron oxide, iron carbide, and a lot of these iron sites are not accessible. Now, another way of doing it is pretty much to start with a precursor that already contains this configuration of a single atom coordinated to nitrogens. And there's many examples, porphyrines and so on in the literature. And then you could exchange this metal here for your metal of choice, for example, iron. So in the literature, people use a lot this Z8. The Z8 has this right configuration of metal coordinated to these nitrogen sites. However, when you carbonize this Z8, which is a MOF, you would collapse most of the pores. You would get a relatively high iron nitrogen single size density, but because of the microporosity, you would not have access to these active sites, and you'll get a poor electrochemical active site utilization. I will skip this slide and I will tell you the way we did it. So we took an organic monomer. This was 3-aminopyridine, and we took magnesium chloride hexahydrate. What happens during the process is that the 3-aminopyridine interacts via hydrogen bonding with this magnesium chloride hexahydrate. You have a liquid state polymerization. You form some magnesium oxide. This acts as a template to form the porous carbon, but at the same time, some of this magnesium would also coordinate to your nitrogen sites from this 3-aminopyridine. So you would form an organic framework that has this magnesium 2+ coordinated to nitrogens. So as I said, you start with this 3-aminopyridine. You work in the presence of magnesium chloride hexahydrate. You form this porous framework, which has this nitrogen magnesium configuration. And then you come at a low temperature and you exchange this magnesium for your metal of choice. You could do iron, you could do nickel, you could do chromium, you could do cobalt, you can do whatever you want. The advantage of this method is they would give you a very high surface area material because you are templating it in situ with this magnesium oxide. And you would see that at 900 and 1000 degrees, this material contains mostly mesopores. And why this is so? Another thing when you do the single atom catalyst is how you characterize this material. So this is quite key. And it's very difficult to prove that you have the single atom sites within your catalysts. So the best method to do this is a combination of methods. So this is called Mössbauer spectroscopy, and it looks at the state of iron, and it tells you which iron is high spin, which iron is low spin. It tells you about paramagnetism or ferromagnetism. And if you work with experts, I know Mössbauer expert, you can learn a lot on how to deconvolute this Mössbauer spectra to figure out if what coordination you have in your iron, and also what state of iron you have. So we learned that mostly we have iron free, about 41%, and that we learned that this iron free is actually coordinated in a penta-coordinated manner, which means that you have these nitrogens, but you have another actual ligand here. And this was also confirmed by X-ray adsorption spectroscopy. So here you need to go to synchrotron and you do some standards. So you do iron, where you see iron-iron bonds. Then you can do an iron phthalocyanine, which has the single iron site, and you do your catalyst. And you see how nice your catalyst is matching with this iron phthalocyanine, which tells you that you have the single atomic site configuration mostly. You could also do extending X-ray adsorption fluorescence spectroscopy, and here you could learn about the coordination number on your side, and this also gives us a coordination number of 5. So that means that we have 4 nitrogens coordinating with an iron, but the iron or the metal is in a 5 coordination state, which means that we can have another type of ligand coordinated to this. It's hard to know what that ligand is, so we went to our collaborator in Denmark, Alex Pager, and he did some DFT calculation, and he figured out that in order to have a good OR performance, to be on top of this volcano plot, potentially we probably have an OH actual ligand, which is coordinated with a pyrrolic type of nitrogen. So we don't know exactly because this is hard to characterize, but DFT suggests that for a best performance, this would be the ligand that we would have. You know, if we want to use the same materials for CO2 reduction, probably the ligand could be good if it would be an amine group. Anyway, we went and applied these materials as catalyst for oxygen reduction reaction. And as I said, we have one that doesn't have any iron coordinated, just nitrogen carbon, the one with iron, and the one with nickel. But the one with iron, what was good about this, so this is a comparison with literature. So here you have the active site density, and here you have the active site utilization. Now, the active site utilization is how many of your total number of active sites will be active towards the oxygen reduction reaction. And the way that you determine this is using a technique called nitride stripping, which gives you the number of electrochemically active sites. And then you divide this over the total number of iron sites that you determine on 5CP. And this is how you're going to learn that in fact, our catalyst does not have a very high number of active site density, but most of the sites that we have are extremely active. 50% of them are very active, which is quite good. And this is in an acidic environment where normally this reaction do not work. So as I said, this works very well. And then to end up the oxygen reduction reaction, I will not give you details, but I said that it's easy to, well, it's not easy, but we could make the single atom catalyst work very well for oxygen reduction reaction, similar to platinum. But already if you look here, this is the initial cycle, and after 1,500 cycle, this starts degrading. So the current is decreasing. And so the problem with this catalyst is that they're not very stable under the real operating conditions that you have in a fuel cell. So that's the DOE target that you have. You need to have a catalyst in your fuel cell that would last more than 1 year. And normally for this commercial iron nitrogen catalyst, they last less than a month. There's only one commercial nitrogen catalyst, and the best reported in the literature catalyst degrades in about, I don't know, 3 months, let's say. So this is not very good. That's why what we did is we coupled a gas diffusion electrode where we have our single atom catalyst layer with an ICP-MS to really try to understand really how this catalyst degrades under real condition. And so, of course, the real conditions are tough. Normally, a fuel cell operates at around 70 degrees, but we also did it in 20 degrees and under unsaturated oxygen atmosphere. So we used perchloric acid as electrolyte, and we really look at the degradation of the catalyst. We did this accelerated stress test, and if you want some more details about this, there's a very good paper from Zelani in Nature Catalysis. Not to mention that, yes, the catalyst degrades. So once you do this accelerated stress test in oxygen at 20 degrees, you'd see how it goes down, and in particular at 70 degrees. And that's also because the surface of your carbon oxidizes quite a lot under these conditions. And so we looked, you know, at the pristine catalyst where you have the nice single sites. And this is in argon where you still have nice single sites, but then in oxygen at 20 degrees, you start seeing these big aggregates, which means that your catalyst dissolves in the solution and reprecipitates. And strangely, at 70 degrees, you don't see aggregation, but you see quite a lot of loss in performance. So this is a very complicated thing. I just wanted to tell you that basically what happens really under oxygen is that your single atom catalysts come together, they precipitate at iron oxide, some of them leak in solution, and some of them reprecipitate back on the catalyst. When you are at 70 degrees, your iron single sides, they change to also iron oxides that might reprecipitate on your catalyst and then leak back into the solution. And we can monitor the concentration of iron in the solution constantly under different potential or current densities. But most of it, you would also have local change in the pH because you're changing the concentration. So you will have massive changes in the pH. You would see from acidic to almost alkaline once this reaction happens, because you have a change in your proton concentration constantly, which will also affect the dissolution of iron. So it's very complicated with the single atom catalyst. As I said, they degrade quite a lot. They form iron oxide, iron, they precipitate in the solution, they reform, the carbon gets protonated, the carbon gets oxidated, and so on. So I think in the interest of time and in order to maybe take some questions, I'll skip all the battery parts today. We are working on making hard carbons from biomass for sodium-ion batteries, but I don't have time to tell you about it. I will be coming to Africa AMRS, so maybe I will then tell you more about my research on batteries. There, if you're gonna be there, I hope you will. And so I'll just finish with thanking all my research group for their amazing work, and the funders for enabling us to do the work. And again, thank you so much for the invitation. And yeah, I will stop sharing my screen and I'll be happy to take any questions if there are any.
Thank you so much, Prof. This is really insightful, and sorry about the time, but I think that we can take some few questions before you go. I apologize on behalf of Prof because Prof is going to go for the next meeting in 12 minutes. So can we have, you can just show by hand and then you can unmute and ask your questions. Then we can take some few before Prof leaves. So go for it. Anyone that is interested to ask a question. Okay, Benjamin, Tommy, go for it. Benjamin, you can ask your question.
He looks like he's in an aeroplane.
Okay, Nomtandazo, please go for it.
Maybe they are muted?
Lebohang, can you ensure that all of them are... Okay, let me try to see if I can unmute you. I'm not able to. Okay, Peter, Prof. Peter Ngene, can you try and see if you can unmute yourself? Okay, Benjamin, you're unmuted. Go for it.
Yes, all right. Thank you so much. Prof, I want to sincerely thank you for this quite informative lecture. Meanwhile, mine is not actually a question, but I would like you to help us with the materials for this session that we just had, because I found out that due to the limited time you had, you just quickly skim through the materials so that we can go through it, and perhaps any other question that we have, we may likely reach out to you via your email or your social media handle. Thank you.
Yeah, I haven't really talked so much about the material development because I wanted to show them in the context of applications. But yeah, we do, as I said, lots of different materials, from porous carbon to non-porous carbon to carbon fibers to metal oxides, porous, non-porous, deposited, loads of different type of materials.
Prof, I think his question is about your slides, if I get it right. So probably he was talking about the slide in a way that they can go through it and perhaps, so maybe it's something that AMRS will reach out to you so that if we can have a PDF type of it, and then so that it can be shared with us.
Right. Sure. Yeah, of course. I thought, yeah, I can send you the presentation. It's also recorded, right?
Yes, we are recording it actually. Nomtandazo, please go for it. And let's be snappy. Then we can have Peter, then we can have Bala in that order. Okay, to optimize the process, Peter, you can go for it.
They don't seem to be able to speak.
Can't you mute yourself?
Hello. Hi.
Oh, okay. Hello.
Hello.
Okay, Nomtandazo, go for it. And then Peter
Am I
can...
unmuted now?
You're
Yeah, we
unmuted
can
and
hear
we can
you
hear
now.
you.
Okay, thank you so much, Prof, for a wonderful presentation. My question is short and straightforward. As you mentioned that you, anyone who comes with a membrane that can replace Nafion can be very rich. Do you have any plans
Oh
on
no,
research for that?
I am not a membrane person, so that's for people that work on polymer membranes. That is not my expertise. That's why I told you anyone that is an expert in polymer and can make it without fluorine and very much proton conductive, similar to Nafion today, that'd be very good. I think there's a lot of demand in this, but I'm not a membrane developing person, so I won't be rich. I hope one of you
Okay,
will
are
be
you willing? Okay, are you willing to collaborate on that maybe in with someone from Africa?
Yeah, of course. If there are people that do membrane research, I'll be very happy to think about it and also help test the conductivity of these membranes. But I don't really have the ideas on, what materials should we use instead of Nafion. So if anyone can make some conductive membranes, I'll be very happy to test them.
Okay, thank you so much. You'll be hearing from me very soon.
Excellent. Okay, Peter, go for it. And then I see Professor Nosipo Moloto. Peter, go for it.
Yeah. Good afternoon, Magda. Nice to see you. Very nice talk. I was just wondering, so on your platinum carbon metal oxide tandem cell, catalytic cell that you showed, where you showed that the activity scales with the acidity, right? So is it the total acidity? And then I did see that you are comparing both carbon and ceria and aluminum. And so my question is about, of course, when you look at this material, they also have other differences, intrinsic differences. How do these other differences, apart from the total acidity, also influences this in terms of porosity of this material? They are quite different and other properties. So, so I was just wondering if you have something to say about it. That's my first question. But we'll see if you can get to the second one.
So we've only compared three materials that are commercially available, which is alumina, ceria, and titania. And because these materials are commercially available, the surface area is really not optimized. And so the surface area for all of them is comparable. They're low surface area materials, there's nothing special about the surface area. So the surface area is quite similar between them. I don't remember, but it's about maybe 100 square meter per gram, around small variations, but no huge variation. And the platinum is needed, so we actually deposited platinum onto these metal oxides. And so, of course, yeah, we looked at the number of acid groups, and I think that is the biggest contributor to the catalysis. But I think it would be nice to, as you say, to take a step back and make our own supports, and make our own with very defined pore size, with a better diffusion, and so on. But we haven't got there. We've really, in that case, we haven't made our material. We just bought everything commercially.
Thank you. And then maybe just one short one is talking about going back to the ionic conductors. So you talk about the membranes.
Yeah.
Do you think that inorganic membranes will stand a chance for this system?
Probably yes. The only problem is that, well, again, I am no membrane person, so I don't know much about membranes. I think the inorganic membranes, they're quite brittle and quite inflexible. And as I said, you have a lot of interfaces. So in order to get the interface between your membrane and the electrode, if your electrode is stiff and your membrane is stiff, and there's two solids, I think you can't get a good interface. But potentially you could look at some composites between inorganics and polymers, maybe.
Okay.
And no fluorine.
Yes, yeah. Thank you very much. Yeah.
Prof. Moloto, please go for it. And I saw Prof. Bala. Prof. Moloto, go for it.
Yes, thank you. I just wanted to ask about your titania and Syria, and you said you bought them, but I mean, surely we can make them. And then there are semiconductors. Do you think that if you were to shine light, you'll improve the efficiency?
Very small question. Indeed, that's another thing we want to do in the future. We want to see how light would also change and affect the selectivity of these materials, and then maybe, use some in operando optical spectroscopy to understand the intermediates and so on. But we haven't done it yet as of yet. Kind of run out of funding on the project, and yeah, I mean, I cannot complain about funding here compared to you, of course, could be hypocritical, but the funding situation at the moment in the UK is not great. But we have elections today, so you never know, might get better. But yeah, absolutely, shining light on them would be a new direction that would be very interesting to follow up. Yeah.
Okay, I'm interested in that area. I do semiconductor nanoparticles. You said you were going to come to Africa. Where? Which country?
Rwanda.
The AM in Rwanda.
Oh, yes. Okay.
Yes, the Africa AMRS from the 16th, I think. Yeah, December. Yeah, I'll make that announcement shortly. Prof. Bala Ngom, Prof, do you have one more opportunity to take one more question? Prof. Bala Ngom, I saw you, man.
Just to tell the previous, but please send me an email, and if you can send me a paper, yeah, it would be nice that we can collaborate as well. I'm very interested collaborating with African countries and look for some common opportunities, of course.
Sure, I'll do that.
And Prof. Moloto, I will just share the email with you right away. Yeah. Okay.
Hola,
Prof.
where
Bala
are you?
No, this one, thank you very much. Thank you. I do not really have a question. I just wanted to thank Titirici for his time, for the engagement that she has on the African Material Research Society. Then all of you guys, as you said, we'll see you on December in Rwanda. Thank you very much.
Yeah, I have someone at my door. Let me just get him in, and I can stay in for a bit. But very nice to see you, Bala.
Good. Okay. At least maybe we can have one or two questions. So we just wait for Prof. Yeah.
Yeah, you can
Yes, is there anyone? Cyril, I saw your hand.
Yes.
Cyril, go for it.
Yes, thank you. Thank you, Magda, and it's really nice to see you. It was a beautiful presentation. I was just going to ask a question about your hard carbon.
That I didn't present it.
Yeah, you didn't present it. I have actually followed some of your papers, and I've also worked on hard carbon. What is actually the property that is of interest? Because the hard carbon I have also synthesized, they happens to be not porous.
That's good. Non-porous is good.
Yes, non-porous, and of course, the I use them as anode materials in lithium-ion battery and in sodium. But the performance of the hard carbons were not so nice. So I was wondering, is there anything one can do to improve the performance?
Well, I think you need to understand the structure to improve the performance. So you need to understand conductivity, the amount of defects that you have, the pore size, the pore volume, the density of your materials. It's a bit of a magic touch, but yeah, I think ideally you want the sweet spot of oxygen defects,
Yeah,
and the sweet spot of interlayer spacing.
yeah.
If you have an interlayer spacing that is too large or too small, it's not good. You
It's not
need
good,
to
yeah.
have an interlayer spacing of about 3.6 angstroms. So you
Yes,
get any characterization of this material.
yes.
But I guess one way of finding out is, well, if they don't work, yeah, I don't know.
Yeah, I think
What
one
I
challenge.
what
Okay,
I would do to them is maybe, what temperature did you carbonize them at?
800. I actually use the thermal
It's too
synthesis.
little.
It's
Too
too,
little.
it's
Too
too late.
little. Yeah, you need to carbonize them at least
At higher.
1000 or above. Yeah,
Yeah,
I think
I
they'll
know.
work better.
I just actually wanted to at least use a lower. I wanted to see whether I could optimize the material at a far lower temperature using different synthesis methods. So that's what I was trying out. But it's okay. I'm still working on the material, trying to still optimize it.
I think optimize them at higher temperature, and if
So,
they still
yes,
don't work, you can tell me to think of the next option.
temperature, of course.
But
Okay.
yeah, I hope to see you. Are you gonna be at the Africa AMRS?
Yes, I will be. Hopefully, I'll be in Rwanda. I hope to see you.
Yeah, me too. I need to figure out my trip. I haven't really planned anything. I probably need a visa. But
Now the visa won't be an issue. I think there's visa on arrival for you.
okay, I'll figure it out. I need to look on how to get there, but should be
Yeah.
fine.
Yeah.
Right.
Any
Yeah,
more?
I think I need to kind of go soon.
Okay.
But if there's anything urgent, I'm happy to.
Yeah.
No. Thank you.
Okay.
Thank you so much, Prof. And on behalf of the organizing committee of AMRS and also this colloquium, we just want to thank you so much for availing yourself and sharing your wisdom and your time with us. We don't take it lightly at all. And we also want to thank all the participants. So, Prof, I think you can, if it's with your kind permission, I think you can go and then I make the following announcement. But it's all about the Africa AMRS. And I've seen that some people are sending me direct message or putting a message on the chat. If you have submitted an abstract and all that, it's currently undergoing review. And then you will be hearing from the team next few weeks. So kindly bear that in mind. They've also put some information in the chat. That is, there is grant opportunities available for students who would want to attend and present their papers or their abstracts. So it's very important that you make do with that. Prof. Bala, do you want to say anything? I know I'm stepping in for Prof. Omolulu, but then he will be communicating with us. And then I must say that these recordings will be sent to all the people that actually RSVP'd. And also, like we said, we'll try and reach out to Prof and get a PDF, and then we can share the PDF with all of you. And then if you have any question, Prof will answer it. I'm actually going to, Prof, with your permission, can I put your email in the chat if that is okay?
Yeah, sure, you can.
Thank
Put
you.
it in the
I'm
chat.
going to do that.
And then also, if you send me some instructions, if I need to do anything for the Africa, because I'm not sure if I receive anything, or sometimes they go to spam by default. I had that problem with Bala last time, which wasn't very nice.
Right.
Send me an email, and if I don't reply, that means I didn't get it.
Okay, no problem. I would communicate that to the organizing committee, which I'm actually a member of it. So we'll just ensure that I've taken note of the comments you made, And then at our meeting, I'll make sure that that is discussed, and then we will share. And this also goes to all the people who have received emails or are waiting for emails. Please drop the Secretariat an email, and then we'll reach out to you. It's also because of the volume of emails that we're currently receiving, but then just give us some few days, and then we'll make sure that we'll reach out to you. On this note, I want to thank you all for attending this particular colloquium. We are really excited in having you. We hope that you will attend next month colloquium, which would also be shared to you. And on this note, thank you so much, and I wish you all of, depending on where you are, good morning, good afternoon, and good evening. On this note, Prof. Bala, if there is nothing from your side, then I would want to adjourn this meeting.
Desmond, thank you very much. I don't have anything to say in that, because I'm not here as the president of the AMRS. I'm just here as a scientist, because I have been collaborating with Magda the last 3 years. Thank you very much.
Right.
Thank you all. I really need to go now. Thank you. Bye-bye.
Okay. Bye, everyone. Bye-bye.